Okay, thank you. All right, good afternoon, good evening, everyone. So we are done with the ELP theorem. Let's just recall the statement. Right, so it says that every matching covered graph that has a non-trivial tight cut has an ELP cut. Right, when an ELP cut is either a non-trivial barrier cut or a two separation cut. Right? And an equivalent statement is the following characterization of bricks. I think this was a DIY in a previous lecture, so make sure you've done it, which says that bricks are precisely the three connected bicritical graphs. And here bicritical includes at least 4 vertices. Right? Otherwise you can have a theta graph with multiple edges, theta being k2 with 3 edges. You can add more edges, that would also be 3 connected and bicritical, unless you insist bicritical graphs have at least 4 vertices. So then that doesn't happen. Right? So these are equivalent. So we have proved both of these. Right? What we will do today, we will look at some applications of the ELP theorem. Right? Okay. Of course, by applications, you know, these are applications of graph theory to graph theory. Yeah. A graph, a matching covered graph is bipartite if and only if number of bricks is equal to 0. Yeah, you all agree? Matching covered graph is bipartite if and only if number of bricks is 0. Question: can we characterize those matching covered graphs for which number of braces is equal to 0? B0 is the number of braces. Right, so most of you probably know the answer. Well, some of you know the answer.
I think we prove the first statement in the course?
Right, it follows from the characterization of tight cuts in bipartite graphs. Right? When we looked at the characterization of tight cuts, we observed that both contractions will be bipartite.
Yeah, okay.
Therefore, it follows that number of bricks will be 0 inductively. Right? So this we have already proved. Yeah, that's a good point. This we have already proved. It follows from tight cut or separating cut characterization in bipartite matching code graphs. Right? But this we have not answered yet. Right? So this is one thing we will answer today. Right? So any guesses? Right? Yeah? Everybody sees it? Maybe I've already mentioned it before. So yes, the answer is indeed bicritical graphs. Let's prove that these are precisely the bicritical graphs. Right? I don't remember the theorem statements, that is why I took out my computer. Yeah. 5.13. Yeah, it's sort of equivalent to 5.13. Anyways, so I'll just put it in quotes. It's not exactly the same statement, but we'll prove this. A matching code graph is bicritical if and only if its number of braces is equal to 0. Okay. Let's see. Forward implication. Let's suppose my matching code graph G is bicritical. Supposing I have a bicritical graph. Well, if it is a brick, there's nothing to prove. The number of braces is equal to 0. So we are proving by induction. If G is a brick, then done. Right? And clearly it has no braces because it's a brick. Right? Now suppose it is not a brick. Well, it is bicritical, so it can't be bipartite, right? Because it has 4 or more vertices, it can't be bipartite. So therefore, it's not a brick, it's not bipartite, therefore it has a non-trivial tight cut. Since G is not bipartite, G has a non-trivial tight cut. So I can take an arbitrary non-trivial tight cut, but I will need the smaller graphs to be bicritical. It's not very clear to me how that is, if that's easy or not. But what we can definitely do, what is much easier in life, is to not take a arbitrary non-trivial tight cut. Right? In fact, see if you can work with a non-trivial tight cut that is arbitrary. I'll leave that as a DIY or maybe TIY because I don't even know. Can we finish the proof? But since I said applications, I will use the ELP theorem. Can we finish the proof? Using an arbitrary non-trivial tight cut. I don't know. But what we will do is we'll take an ELP cut. Because this is a non-trivial tight cut, by the ELP theorem, there is an ELP cut. Is that okay? That I know how to finish the proof. By ELP theorem, G has an ELP cut. Can G have a barrier cut? It can't have a barrier cut, right? Because G is bicritical, so there is no non-trivial barrier. So therefore there is a two suppression cut. By ELP theorem, and since G is bicritical, we conclude that G has a two suppression cut. Yeah, there's a two suppression cut. Let's make a drawing. In fact, I want to introduce a concept that is relevant to Santosh and Rohini's work. So there is a two suppression cut. It looks like this. Well, but forget two suppression cut. There is a two suppression in particular. In particular, G has a two suppression. Let me call it S equal to U comma V. These are my two vertices, U and V. This is a two suppression. When I delete these two vertices, G minus U minus V, I get a bunch of even components, at least two, possibly more, right? And this would be a two suppression cut. This would be a two suppression cut. So I can either take a two suppression cut and draw the two contractions. But I want to do it slightly differently. Rather than drawing the two contractions, I want to take the following graph. This is related to a concept we learned in SGT. I will take the graph induced by this part, whatever this part is. This could be a bunch of components, and these two vertices, and I will add an extra edge called the marker edge. Okay. So what we'll do is we will take what we call the marked S components. There's a problem. It is correct if it is only two components. But if there is 10 components, I am taking some components here, some here, and now I am calling the marked as components a slightly more general thing than before. Right? I'll take 5 components and UV, take the subgraph induced by them, and add an extra edge. Okay? So this is sort of generalized marked as components. I won't define them. Right? So I'll take the graph induced by all these vertices and I will add an extra edge, and I'll do the same thing here. The extra edge I will color it using different color. Right? So this is my graph G1, G2, and the extra edge, the so-called marker edge, has been added here, and there is marker edge here. It is possible that the original graph has 5 edges joining these two, in which case now I have 6 edges joining these two. Right? I claim that G1 and G2 are isomorphic to the tight cut contractions up to multiple edges. I claim that if you take any tight cut C, either this one or this one, I claim that G1 and G2 are isomorphic to the C contractions in fact the only multiple edges that will differ will be the number of edges here actually. except up to multiplicities of marker edge. Convince yourself.
Exactly one edge.
Right, only this. This is the only place where difference will appear. Everything else will be the same. Yeah? Okay, fine. Alright, so therefore, basically these are matching chord graphs because these are isomorphic to the tight cut contractions up to multiplicities in this particular edge. So there is always an edge. By the way, observe that here there is an edge joining them, and in the C contraction also there will be an edge joining this vertex to the contraction vertex. There will always be, if you take the C contraction, if you shrink this into single vertex, there will be a edge between the shrunken vertex and this vertex. Right? Therefore, this is a true statement. Right? Yeah. Alright. So therefore, these are actually the same as the tight cut contractions. There is no difference between the generalized marked as components and the tight cut contractions in this case. You all agree? Okay. Let's go back to what we are trying to prove. We are trying to prove that for a bicritical graph, number of braces is 0. We want to finish the proof by induction. So what should we do about G1 and G2? We should prove that G1 and G2 are bicritical. We should prove that G1 and G2 are bicritical, and then we are done. DIY, not difficult. G1 and G2 are bicritical. Therefore, by induction hypothesis, the number of braces of G1 is 0, number of braces of G2 is 0, therefore the number of braces of G is 0, because these are just tight cut contractions. Right? We are done, finish. Right? So, yeah. By induction hypothesis, number of braces of G1 is equal to, number of braces of G2, and both of these are 0, which basically implies that the number of braces of G are also 0. Right? And of course, Lovaas's uniqueness is used everywhere, right? I mean, it is used the moment I use this notation. Right? So I won't say that we are using Lovaas's tight-cut decomposition theorem because it's always there. Right? You basically can't do anything without that theorem. Alright? So done? Are we okay with this direction? Everybody is convinced? Forward direction is done. The only reason I did this way is because in some sense, when you prove that they are bicritical, these multiple edges actually don't matter. In some sense, this is a bit easier to visualize, in my opinion. Rather than drawing the contractions, in the case of two separations, the marked as components are somehow easier to visualize. And the point is, they are as good as the tight cut contractions. In fact, the marked as components played a very important role in Rohini's work on theta free graphs. The characterization of theta free graphs, whatever that means, fundamentally relied on marked as components, and since then Santosh has also used it for getting consequences of those characterizations. Right? So it's, yeah. Anyways, okay. Questions, concerns with this direction? Yes, go ahead.
How is this become easier when we use markers?
Oh, in this context, it doesn't matter a lot. I'm just saying that in a certain sense, it's easier to visualize the marked as components rather than shrinking the shore. But yeah, in this particular claim, it doesn't really matter. In this DIY, it doesn't really matter. All I'm saying is that visualization is a bit easy. Yeah. Yeah. In fact, what you can also do is you can draw 10 components and look at any marked as component and prove that it is bicritical. But we don't need to do that. We can just put some components here, some here, and then prove it. Yeah. Okay. Alright. So that's one direction. But yeah, as I said, you don't actually need this generalized marked as components concept. You can directly go with tight cut contractions and it's as easy as the other one. Yeah. Okay, so this takes care of one direction. Now let's look at the other one. Supposing the number of braces is 0, then we need to prove that the graph is bicritical. Let me make some space. Now suppose that number of braces is 0. Yeah. We want to prove that the graph is bicritical. Well, if the graph is a brick, then anyways it is bicritical, because we proved ELP theorem 2 versions. Bricks are 3 connected bicritical. So, if G is a brick, we are done. Yeah. So now we can assume that G is not a brick. Well, G is also not a brace, because number of braces is 0. So it can't be a brace. So G is neither a brick nor a brace, therefore it has a tight cut. Otherwise, G has a non-trivial tight cut. Yeah. So consider, in this case we'll actually not even use the ELP theorem. Let's see if it works. So take a non-trivial tight cut, take any arbitrary non-trivial tight cut, C. Okay. And let G1 and G2 be the C contractions. Of course by induction. Well, number of braces of G is 0. So therefore the number of braces of G1 and G2 are also 0, right? You all agree? Well, therefore by the induction hypothesis, these two graphs are bicritical. You all agree? And therefore G is the splicing of two bicritical graphs. DIY, maybe it was already done in assignment 1. Thank you. Yeah. By induction hypothesis, G1 and G2 are bicritical. By assignment 1, since G is a splicing of G1 and G2, G is also bicritical. So this brings me to a point why the assignments have been so long so far. Because if I don't put everything on the assignments, then I cannot use things from the assignment when I want to prove things in the lectures. But anyways, so that's one of the reasons. That's one lazy reason to make the assignments long, so that whenever I need something in a future lecture, you can just tell me, oh, we did this on assignment. So fine. Anyways. Sorry?
It's a DIY for group 3, I think.
Oh, it's a DIY for group 3. DIY? Or you mean assignment problem?
Yeah.
Oh, for group 3 it was not part of the... okay. It was only for groups 1 and 2. Yeah? Okay. Yeah. You don't remember doing this. Well, now you can do it.
This, we don't even need this, no?
Why?
The contrapositive is much easier.
The contrapositive is easier?
Take a barrier.
Um,
Take a barrier.
Yeah, take a non-trivial barrier and the core will give you braces.
Ah, I see. Okay, so you are saying that for this direction, prove the contrapositive. Um, suppose the graph is okay. We're putting this direction. So I'm not going to assume this. I'm going to assume that the matching code graph is not bicritical. Ah, okay, that's a good point. Yeah. Suppose the graph is not bicritical, then there is a non-trivial barrier. And now consider all the non-trivial odd components with respect to that. That is a laminar family of tight cuts. So I'll get a bunch of graphs called the B fragments. But I will also get the core, which is bipartite. But bipartite graph will give me braces. Therefore, the number of braces is greater than 0. Good point. Yeah, that's another way to do it. Thank you. All right. Okay. So yeah, contrapositive doesn't require assignment 1. Thank you. Yeah, if the number of braces is 0, we prove that it's bicritical. If it's not bicritical, then there's a non-trivial barrier. Yeah, works. Thank you. Good. Alright, so that's our first application of the ELP theorem. Now we know what are those matching code graphs that do not have any braces. They're exactly the bicritical graphs. That's kind of nice. Bipartite is the bricks being 0, bicritical is the braces being 0, number of braces being 0. Who would have thought? Anyways, okay, good. So that's the first application. We have enough time, right? We are going on till 8 p.m. So let's keep going. Yeah? Alright. So the next application.
I have another
Go ahead.
question.
Yes.
Is the converse to the assignment 1 problem called?
Converse. What is the converse?
So you have a bicritical graph. Oh wait. Yeah, then the tight cut has to be.
Right. So now it follows that for a bicritical graph, if you take any tight cut, then the two contractions will be bicritical. We did not, yeah, here it was a TIY.
Yeah.
This TIY is what you are asking.
Right.
Right? But now if you assume this theorem that we proved just, then it follows that for any tight cut, the two contractions will be bicritical. But yeah, in general, if you take an arbitrary tight cut, I have not tried proving it, or if I have, I have forgotten. Right? So give it a shot, see what happens. Yeah. So yeah, assuming this theorem, it follows. But without proving this theorem, can you directly say, take a tight cut of a bicritical graph, arbitrary tight cut, and prove that both contractions are bicritical? Not sure. Okay. Okay. Any questions, concerns? If not, we will move on to the next application. The next application has to do with cubic graphs. Okay, theorem 5.8. it turns out that in a cubic matching covered graph, which is the same as two connected cubic graph, every tight cut is a 3 cut. And therefore, by a theorem we have already proved in the past, it will then follow that every tight cut is actually a barrier 3 cut. Right? But what we will prove is it's a 3 cut. In a two connected cubic graph, every tight cut is a 3 cut. Right, so let's look at some consequences of this. We'll prove this, but before that, let's just if you prove this, then it follows that in a two connected cubic graph, every tight cut is in fact a barrier 3 cut, because every 3 cut is a barrier cut that we proved earlier. So therefore, it will follow this. This will follow, right? Okay. Next, this also we discussed earlier briefly. We say that a two connected cubic graph is essentially 4 edge connected if it has no non-trivial 3 cuts. So what is essentially 4 edge connected? Cubic graph it is a two connected cubic graph which has no non-trivial 3 cuts. All 3 cuts are trivial ones. This is the reason they are called essentially 4 edge connected. Essentially 4 edge connected should mean that there are no 3 cuts. Well, it's a cubic graph, of course there are 3 cuts. Every trivial cut is a 3 cut. But these are the only ones. That is why we call them essentially 4 edge connected. Excuse me. In Lucchesi-Murthy, they actually assume 3 connected. DIY. The only difference is cubic C4. What is cubic C4? It is this graph. It is C4 with extra edges to make it cubic. Not a great edge. So if you put 3 connected, then this will stop being essentially 4 edge connected. Everything else will be the same actually. So DIY cubic C4 like this. This is the new notation. Cubic C4 is the only such graph that is not 3 connected. Otherwise, yeah. So therefore, in Lucchesi-Murthy, they use 3 connected cubic here, and they don't consider this to be essentially 4 edge connected. Fine.
Sorry, what do you mean?
Yes. Such, by such I mean it is the only essentially 4 edge connected cubic graph as per my definition that is not 3 connected. Yeah. So by such I mean the underlined thing. Thank you. Good. Yeah. And now it follows that essentially 4 edge connected cubic graphs are therefore blah or blah. Yeah, they're all bricks or braces because of this theorem that we are about to prove. So we get a corollary. Yeah, 5.10. Every essentially 4 edge connected cubic graph is either a brick or a brace. Okay, good. So assuming we prove this is proved. Yeah, okay, so we are still to do this. What else? Interesting point is, you may say, is the converse true? Is it true that a two connected cubic graph, if it is a brick or a brace, then it is essentially 4 edge connected? Well, that's not true, right? You all see the obvious counterexample that is staring at you. Can you think of a two connected cubic graph? It should be a brick or a brace, but it should not be essentially 4 edge connected, right? You all see it, right? It's the graph that I draw the most. I think that can be quantified. Right? The graph that I draw the most. Yeah. Right? So, triangular prism. Triangular prism is a cubic brick that is not essentially 4 edge connected. What about braces? Can there be a cubic brace that is not essentially 4 edge connected? DIY, I will come over. So here is a quick DIY. Does there exist a cubic brace that is not essentially 4 edge connected? Okay, think about it. I'll come around and talk to you. Let me know if you have an answer. Okay. It may be related to some problem on the assignment 2, I think. Assignment 2, was there a problem to prove that every separating cut is every 3 cut is a separating cut? Not in assignment 2? Assignment 1? No? Nowhere? Okay. 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 Let's see. I also have to think about it. Yeah, I think I use that fact. It's not an assignment 2, huh? Strange. I was hoping it would be there.
I looked it up again.
Okay, so here is a quick DIY. In a two connected cubic graph, every 3 cut is a separating cut. See if you can prove this. This DIY is related to this DIY. And observe the differences between these two. This is saying every 3 cut is a separating cut. This is saying every tight cut is a 3 cut. They're not saying the same thing in particular. Every separating cut need not be a 3 cut. Peterson graph. Right? Peterson graph is a 5 cut. That is a separating cut. It's not a 3 cut. But every 3 cut is a separating cut. See if you can figure that out. If you have an answer, let me know. I'll come and talk to you. Okay, let me know if you've seen it. Make a drawing. Make a drawing of a 3 cut and draw the 2C contractions. Drawing helps a lot. Whenever you are stuck, make a drawing.
Is there a way around that? Because before you wrote this down, I was trying to take any 3 cut, and I could not even convince myself why the contractions are also bipartite. But if I use this,
yeah, without using that. This is so straightforward that it's like.
okay. But there is, the question is, yeah, it comes down to, is it possible to get a bipartite graph when you're splicing a non-bipartite graph, at least one? There I know the answer, but without using matching theory, if I look at only graph theoretically about cubic graphs, then I'm not able to convince myself.
Right. Well, I mean,
Take in a bipartite to connected bipartite.
cubic.
Cubic, yeah.
Cubic is very crucial.
Then why should the contractions be bipartite?
So if you have not proved, so right, 3 cut is a separating cut, means that you have to prove that the contractions are matching covered. But before you go to matching covered, do you see something more basic about the contractions? They are cubic. Cubic is clear because it is a 3 cut and the original graph is cubic. So the contractions are cubic. Well, what does matching covered mean? in the case of cubic graphs? It simply means two connected. It simply means two connected. So that's the way to think about it. You don't have to think about matching covered. The idea is to not think about matching covered. Right? So you get the two contractions are cubic graphs. That is clear because it is a three cut. They are connected is also clear, right? The two contractions are connected, right? Because a three cut will be a bond. If the three cut is not a bond, then you will get a contradiction to two connected. So the three cut is a bond. The two contractions are going to be connected graphs. That is clear. If you just show that they are two connected, then you are done. Then it is matching covered. So how can they be not two connected? For that you use a fact from SGT. In cubic graphs, blah equals blah. Right? In not just cubic but max degree 3. In max degree 3 graphs, blah equals blah. What are the two? Well, blah equals blah prime. Chi equals chi prime. Chi? No, not chi. What is the word used? Kappa. Kappa. Kappa equals kappa prime. Vertex connected is equal to edge connectivity. Now it's much easier to see. If the graph is, if the contractions are not two connected, then it means that there is a cut edge. It's a cut edge in the contraction. Go back to the original graph. Cut edge will be there in the original graph. Right? So therefore, this is done. Now think about this. Supposing you have a two connected cubic graph that is not essentially 4 edge connected, then can you conclude that it is not a brace? It is not essentially 4 edge connected, therefore there is a non-trivial 3 cut. Well, non-trivial 3 cut is a separating cut, but this is a bipartite graph, therefore it is also a tight cut. Well, therefore it is not a brace. So everything comes together. A two connected cubic graph, bipartite graph, is a brace if and only if it is essentially 4 edge connected. So in fact another consequence, in fact now I can also drop two connected, because for bipartite connected implies, bipartite cubic connected implies two connected. A connected bipartite cubic graph is a brace if and only if it is essentially 4 edge connected. Yeah, lazy. Essentially 4 edge connected. But in the case of non-bipartite graphs, this is not an if and only if statement. Okay, good. Questions, concerns? Yeah, because they don't allow cubic C4, they have to put order 6 or more in this statement. But because I allow cubic C4, I don't need to put that. It works. Okay? Alright. So these are some consequences of this theorem that we are yet to prove. So now for the rest of the Next few minutes, we'll try to finish proof of theorem 5.8. Are there any questions, concerns regarding any of this? No, all good? Okay, copy. Yeah, this is. Okay, so next is to prove this theorem. And we'll use the ELP theorem. We want to prove that in a two connected cubic graph, every tight cut is a 3 cut. Yeah. So let's actually finish a proof of this using Laminar ELP theorem, which we have not proved. Then we will prove using ELP theorem. Yeah. So we want to prove that every tight cut is a 3 cut. Well, trivial cuts are clear, right? Now let's go to the ELP cuts. Barrier cuts. Can you all think about barrier cuts? Draw a barrier in a two connected cubic graph and count. Think about barrier cuts. Draw a barrier. 5 vertices, 5 odd components, if you like, 5, right? And think about the number of edges leaving any odd component, given that the graph is two connected and cubic, right? And given that you have already done STT, assignment 5, problem 5. Right. So how many edges will leave each component? Right? It's clear, right? The only way for this counting to work is for all the odd components emitting 3 edges into the barrier, right? And the barrier vertices emitting 3 edges outside. That's the only way it can work, right? So therefore, we are done with barrier cuts and tight cuts. Trivial. Well, trivial cuts are barrier cuts. So I'll just say barrier cuts done. They are 3 cuts. 2 separation cuts. Let's draw 2 separation cut in a 2 connected cubic graph. This is my 2 separation UV. Complete the figure. There are some number of even components here. There are some number of even components here. If you like, just think about one even component for now. In fact, can there be more? I don't know. Right? And the graph is 2 connected and cubic. See if you can make progress in this case. If you have figured out something, let me know. I'll come and talk to you. See if you can make a graph like this. What about two separation cuts? Yeah. Did you get the other one? Okay. Okay, so the point is that there are not too many possibilities. But you have to use the fact that the graph is cubic. Right? And cubic gives you some nice things. For an even set of, for a set of vertices of even cardinality, what can you say about its partial, the number of edges leaving that set? Given that the graph is cubic, that is something you should use. Right? So it's a standard parity thing. Right? And if you use that, then you see that there are only two possibilities to complete this drawing. Right? So what is clear, what is very clear without doing anything, is that there is one edge like this, there is one edge like this, there is one edge like this, there is one edge like this. This much is clear. Right? But right now these two vertices are not cubic. I still have to make them cubic. But now there are parity restrictions. Because this is an even number of vertices. This is an even number of vertices and the graph is cubic. Right? So, okay, so now I'll come again. This is what? Yes. able to complete this drawing. So can you put more edges?
Yeah, so in the way I have to put it like
This, yeah,
I have to like this.
right.
And only one of
But if you put this one, now you have 3 edges in this cut. Is that possible? So if you put one like this, then you have to also put one like this.
One like this, yeah.
Put it, cut, put it. Now you see 3, 3. But there is one more possibility.
Yeah, from there also.
You are assuming that they are non-adjacent. They could be adjacent, right? So the 2 vertices could be adjacent, in which case you get one more possibility, right? So basically this is what happens. If the 2 are adjacent, you are done. These are 3 cuts. If the 2 are not adjacent, well, I have to make it cubic. So I have to throw one edge from here or here into one of the sides. Let me throw this here. But now I have a cut with only 3 edges, but number of vertices is even. That's a problem. I need a 4th edge. That's it. Again 3 cut, 3 cut. There's another way to do it, which is to observe that every 2 separation cut is actually also a barrier cut. This 2 separation cut is also a barrier cut with respect to some barrier. Then you can just go back to barrier cuts. So that's at least a couple of ways to finish it. You can observe that every 2 separation cut is a barrier cut, and then you are done because you are done earlier. Or you can analyze the cases and observe that in all cases 2 separation cuts are also 3 cuts. Okay, so multiple ways to finish it. So 2 separation cuts are also done. And here's a quick DIY. Prove that in a 2 connected cubic graph, every 2 separation cut is also a barrier cut. Yeah, that's another way to finish it. Yeah. Okay, so therefore ELP cuts are done. ELP cuts, including in this case the trivial cuts. Anyways. So now it remains to prove for the non-ELP cuts. Let's finish using the Laminar ELP theorem, DIY. Finish proof from here using and assuming, because we haven't proved, right? Remember the Laminar ELP theorem. Given any non-trivial tight cut, there exists an ELP cut such that the 2 are laminar. This we haven't proved, right? A significantly harder proof. It's not even included in the book. Right, so see if you can use that and finish off the proof. Then I'll come and talk to you.
We have stated this theorem before?
I stated it. Yeah. I can also quickly just write it. See if you can finish it using this. Yeah. Okay. Good. Anyone else? We are almost there.
Drawing the three edges is actually not clear. This is really clear, right? Just where you draw. Doesn't matter. Because it's really ELP in the corner. This is the ELP program, ELP cursor. Very nice.
So this is what you can have.
Exactly the same.
So here 3 like that.
Right. Now finish the program. Now actually I can say this. The child inside this side. Yes, definitely. Yes, the cubic graph. This is still going to be trigonometric. Yeah, smaller graph.
Okay, good. So yeah, so everybody sees it, right? So if you have a non-trivial tight cut, if it is an ELP cut, you're done. If it is not an ELP cut, then there is a cut laminar to this one. That is an ELP cut. That one is a 3 cut because we just proved that ELP cuts are 3 cuts. That one is a 3 cut. Now you shrink this shore. This is still a tight cut in the smaller graph. Therefore, by induction, it is a 3 cut. But then it is also a 3 cut in the original graph. Right? So done. Right? So using Laminar ELP theorem, you're just done. But the point is, we have not proved the Laminar ELP theorem. So we will do it using the ELP theorem. Okay, so now let's see denote a non-trivial tight cut that is not an ELP cut. Our goal is to show that C is a 3 cut. Well, this is a tight cut that is not an ELP cut. By the ELP theorem, there is an ELP cut. There exists an ELP cut. Say D. Now there are two cases, C and D are laminar, in which case you just finish the proof yourself, or they are not laminar, right? If they are laminar, then you just finished it. If C and D are laminar, DIY using induction. Right? Now suppose they are not laminar. This is the interesting case. This is where laminar ELP theorem cannot be used because they are not laminar. Now suppose that C and D, well, they are not using it, that's the point. They are not laminar. So they cross. They are crossing cuts. Let's make a drawing. Right? By now you are very familiar with this drawing. C is my pink cut, D is my blue cut, something like that. C, this is D. They are crossing cuts. One of them is a 3 cut. One of them is a 3 cut, right? D is a 3 cut because it is an ELP cut. We just proved that ELP cuts are 3 cuts. So D is a 3 cut. And we also get 2 more cuts. I won't write down too many things. I'll just write down odd, even, odd, even. And let me remind you of the cuts I and U. I is this cut, U is this cut. We know that D is a 3 cut. Now can you finish the proof? DIY. Finish using induction and uncrossing lemma. Okay, try it and let me know when you have done it. Okay, write it. Easier for me. Maybe I'll add a hint. Induction to conclude something about I and U. And then uncrossing lemma to conclude the final thing. Well, technically, uncrossing lemma has to be used for. I mean, we already know that I and U are tight cuts. So, to deduce that the cardinality of the original cut C is 3.
Actually, we use Consequently in the second step. Yes, one is non-trivial, we obtain using induction. Other things, it's just a two separation system. We have already done with ELP.
What are you done with non-trivial? I didn't get it.
Let's say I is non-trivial,
Yeah.
then the score I is non-trivial.
Yeah.
I shrink it all into a single vertex. Now C is, I don't know I is treated or not. Sorry, I can conclude that using D. Right. And shrink the other side of D. And now I has to be a triplet.
D is on 3, right?
Right side of D.
Yeah.
And I
Is it right?
triplet.
Because of the
Yeah.
yes.
Now I shrink I in the big then C is there. C goes a tighten smaller to contain the big. So C is a 3 cut. And now in the case where both our components are 3, now it's a 2 separation. But maybe you have something slightly different.
It's not too different, but yeah, it's slightly different. Yeah, I was not going to go to separation case. You can directly conclude that I and U are tight cuts. It's non-trivial tight cuts. Or trivial also, I don't care. They are tight cuts in smaller graphs. Each of them is a tight cut in some D contraction. But D is a 3 cut. So therefore they are tight cuts in smaller topological flavor. I and U.
Okay.
Therefore there are 3 cuts. I and U. How do you use the fact that C plus B is equal to A plus B?
I don't even know this.
So there are multiple ways to finish the proof from here. But yeah, if you have any ideas, let me know. Okay. Okay.
What you will considering all cases here. So D is a 3 count. Can you make a drawing again? Yeah. Okay. What is C and D? Okay. Yeah. Okay. Okay. Is it cubic? This is a 3 cut, so this is fine. And then it was shrinking. Okay. This is not a cubic. Okay. I see, including the is 3. Okay. So you use also 3. Now we can use an equation.
So the point is, can you somehow conclude that I and U, each of them have cardinality 3? Right? Using induction. Can you say that I and U are tight cuts in some smaller cubic graphs? If you get a smaller cubic graph and I is a tight cut there, then by the induction hypothesis, cardinality of I is equal to 3. That would be nice. Same for U. Can you get a smaller two connected cubic graph where U is a tight cut? Then you can again conclude by the induction hypothesis that cardinality of U is equal to 3. Can you do that? Then we'll think about cardinality of C. And you know that D is a 3 cut. That is very important. D is a 3 cut because D is an ELP cut. That we already know is a 3 cut. So, first conclude that cardinality of I is 3. Then conclude that by the same argument, by the similar analogous argument, cardinality of U is 3. And then finally conclude that cardinality of the desired cut C is 3. See if you can follow these steps. D is a 3 cut.
smaller to connected cubic.
Yeah.
This is a tight cut.
So this is 3 cut.
Right? So let's complete the first step. Observe that if you shrink this shore, the right side of the blue line, into a single vertex, well, that's a two connected cubic graph because this is a 3 cut. It is a tight cut. You shrink the shore, you'll get a smaller matching chord graph, and because it is a 3 cut, it is also cubic. So you've got a smaller cubic matching chord graph, which is the same as two connected cubic graph, and I is a tight cut there. You don't have to worry about I is trivial or non-trivial, irrelevant. It is a tight cut in a smaller two connected cubic graph. Therefore, by the induction hypothesis, it is a 3 cut in that graph. Well, if I is a 3 cut in that graph, I is a 3 cut in the original graph. Right? I is the same I. Not I, but I. Right? So you have I is a 3 cut because it is a tight cut in a smaller two connected cubic graph. Analogously, U is a tight cut in a smaller two connected cubic graph. So cardinality of U is also 3 by induction hypothesis. So basically the point is both I and U are tight in some decontraction. For I will shrink this shore, for U I will shrink this shore. Right? And therefore, but decontractions are smaller two connected cubic graphs. So by induction hypothesis, we can conclude that cardinality of I is equal to 3 and cardinality of U is also equal to 3. Okay, so that's good. Now remember, there are no edges going from here to here. And that leads us to a counting thing that we did earlier once upon a time. Right? Cardinality of C plus cardinality of D is equal to cardinality of I plus cardinality of U. This is because there are no edges going from here to here. So all the edges are counted exactly the same number of times on the LHS and on the RHS. These are 4 types of edges, and there's the 5th type of edge. This one is the one that is counted twice on LHS as well as RHS. Whereas the other 4 types of edges, they are counted once on both LHS and RHS. So you're counting the same thing. Right? So therefore we have this. Well, this is 3, this is 3, this is 3, and the only way this equation can work is this is 3. Right? So we are done. So we have proved without using the Laminar ELP theorem, but we have to use Uncrossing Lemma. Yeah, so all tight cuts in two connected cubic graphs are indeed 3 cuts. It's very nice because now we get all of these corollaries. And in fact, another point I want to mention is that for a two connected cubic graph, you can do the tight cut decomposition and you will get the exact same list of graphs. You don't even have to say up to multiplicities of edges. You will get smaller cubic graphs. I do a tight cut decomposition, I'll get some cubic graphs, bricks and braces. Santosh does it, Santosh will also get cubic bricks and braces. Well, cubic bricks and braces, if they are the same up to multiplicities, they are the same without multiplicities. Multiplicities don't matter. Right? Yeah? You agree? So in this case, you don't even care about multiplicities. You will get exactly the same list of graphs. Yeah? Okay. So that's good. So I was thinking maybe I could start the next chapter, but I think I won't do that. I will just try to, maybe we can take a short 5-minute break and then continue for like 15 minutes and finish off. On Wednesday, we will start the perfect matching polytope. Using the perfect matching polytope related results, we can actually prove these results in a different way. Yeah, but I don't think I'll start it today because we are almost at the end. So let's just take a 5-minute break and then finish off in 15 minutes or so. Yeah? Okay, thank you. This can't be paused, right? Okay, so this is going to be a bit asymmetric. Okay, that's fine.